I just need to reshare the recording. Okay. So we have gone through the basics of caches. We've gone through handling writes. I've removed this example cache. And then now we're going to move on to measuring and analyzing cache performance, as well as looking at different kinds of caches. So we're going to get into set associative caches today. So cache performance. So just so that we cover all of the terms, there are 3 different kinds of cache misses. The first is a compulsory miss. This is basically there was no chance for it to be in the cache because the cache starts empty. Right? Like it was the first time I'm ever accessing this block of memory, so there was no way for me to really know beforehand that I needed to put this into the cache. But you'll see in one of your presentations that that's not exactly true. There is prefetching. So, but you would still call those compulsory misses if your prefetcher wasn't correct. There's also capacity misses. Basically, the cache cannot contain all of the blocks because it is smaller in size than the memory, right? So that means that you filled up your cache, and so basically the only way that you could have had this be a hit was if you had an infinite size cache, or your cache size just needed to be a little bit bigger. And then there's conflict misses. So this is when you didn't fill up the cache since your last reference, but now I'm referencing a memory location that conflicts with a existing memory location that I want to access later on. So if I was evicted from the cache, not because of capacity, but because of a conflict, then when I come back and want to access that memory location again, and it comes back as a miss, that's a conflict miss. Okay. So here we want to measure cache performance. So this is our equation. So CPU time is clock cycles times cycle time. Basically the number of cycles times how long the cycle is. Now we can break this up into something like this. So we have program execution cycles plus memory stall cycles. And that's our total clock cycles. Okay. So to get our memory stall cycles, this part of the equation, we can take the memory accesses, the total number of memory accesses for the program, multiply it by the miss rates, because basically that means of all of the memory accesses, I missed this portion of them. And then for each one of those misses, I have this miss penalty. So I've stalled this many times. So this can also be broken down to something like this. So your total instructions for the program times your misses, like the number of instructions that resulted in a miss, times the miss penalty. So this miss rate is misses per memory. That makes sense? How do I calculate the number of memory stall cycles? Right? You guys need to understand this.
Yeah. Would you have to remember that, or will be given?
You need to remember. You can put it on your cheat sheet. Oh, but you'll do. The homework has this as a practice problem as well.
Okay.
You'll see it again, but you in order to do the homework, you should understand this. All right. So now we want to do the same evaluation, but rather than just looking at the number of clock cycles, I want to think about it in terms of my overall CPI for a program. So remember, our CPU time is also the CPI times instruction count, which gives us the total clock cycles, okay, times cycle time. And again, we can split up our CPI into multiple different components. But one way we can do it is we can call everything else base CPI, and then we can just think about the increase in CPI due to memory slice. So here, and also break it down further, where we have the pipeline stalls that increase our overall CPI, and then the branch hazard stalls that increase our overall CPI. So we have multiple different components that make up our overall CPI. Right? So here's how we're going to calculate our MCPI, or our memory impact on CPI. Right. So basically, our memory CPI is the number of cycles per instruction the processor is stalled waiting for memory. So it's essentially the same thing that we calculated before with clock cycles, but now it's per instruction. So to get this, we're going to get the accesses to memory per instruction, which is basically just the portion of your instruction counts that are load words or store words, right? Times the miss rates, times the miss penalty. And this will give you your MCPI. So this is assuming the pipeline stall on read and write misses have the same miss penalty, and cache hits require no stalls. But if we have a different instruction and data miss penalty or miss rates, we will have to split it up into two different sections, one for the instruction cache, one for the data cache. But it's the same exact formula. How many instruction cache accesses per instruction do I do? What is this? What is this portion? How many times do I access instruction cache for each instruction? One. Yes. Do I ever get an instruction without accessing the instruction cache? No. So this is 100%, right? So just one. You have this instruction. And then the instruction cache miss rate would be given to you, and the instruction cache miss penalty may be given to you, but you may need to calculate this. In the homework, you will need to calculate this. Okay. So data cache, this is not exactly one, right? So data cache accesses per instruction. This is the portion of load words and store words in your instruction manual. Okay. So this would have to be given to you. Data cache miss rates will be given. Again, you can be given data cache miss penalty, or you may need to calculate it. So the way you need to calculate it is, say you're given how much time it takes to fetch the data from main memory, and you're given the cycle time of the processor. Then you can basically calculate how many cycles does it take for that data to get loaded. That's your penalty. Okay. All right, so these are our components again. So just as a reminder, clock cycles is memory access for the entire program times miss rate times miss penalty. And then if we're talking about the CPI increase, it's the portion of memory accesses over all of the instructions times the miss rate times the miss penalty. And this formula for the CPI is the same for all of our different components. So same for pipeline stalls. You're going to get the portion of instructions that cause a pipeline stall, that can possibly cause a pipeline stall, the portion of instructions that do cause that pipeline stall, times what is the penalty. So that's for your data hazards. And then here, the same thing for branch hazards. What portion of your instructions are branches? What is the mispredict rate? And what is the mispredict penalty? For our end pipeline, our miss penalty is how many cycles? You guys know this. We spent 2 lectures on this. So it was originally 3 cycles because we didn't resolve until the end of executes, so the beginning of memory. But then we moved all of our hardware to the decode stage and reduced our penalty to 1 cycle, right? Because we moved it up 2 cycles. So it was 3 before, moved up 2. Now we have 1 cycle penalty.
So will the miss penalty always be 1 then?
Yes, the miss penalty is 1 cycle. Because now basically you're just getting what portion of my instructions are branches, and then of that portion of instructions that are branches, what portion actually has a mispredict? Because if it's a correct prediction, there's no stall. And then how many times do I need to solve for that? Okay. All right. So again, this is it split up if you have instruction cache and data cache. All right, here is an example. So I have iCache miss rate of 2%, Dcache miss rate of 4%. My miss penalty is 100 cycles. My base CPI is 2, and load and stores are 36% of my instructions. So here are my stall cycles. So this is my miss rate. This is my penalty. This is my number of instructions. And then for the data cache, this is my data cache miss rate. My penalty is the same, but I don't access the data cache for every instruction. I only access it for 36% of instructions. So this is the total number of memory stall cycles. So then we can add them together. So we get 3.44 times instruction counts is our stalled cycles. And then if we want to think about it as the CPI increase, we divide by the total number of instructions. And here it's 2 plus 2 plus 1.4, because when we divide by instruction count, it cancels. So our CPI that we've calculated with our cache performance is 5.44. So versus an ideal CPU that has no stalls from memory, that ideal CPU is 2.72 times faster. So now this is your poll. If you have a base CPI of 1 instead of 2 with the same question from before, how does our overall performance change?
The code.
The code is 658. Okay, I think most of you have answered. We are close to the threshold, so we can just go over this together. So I will go over this. What? So here, so if we reduce the ideal CPI from 2 to 1 without changing the clock rate or memory system, then the CPI becomes, instead of our 5.44, it's going to become 1 plus 3.44, which is 4.44. But then when we compare to the CPU, the ideal CPU, rather than dividing by 2, because it's a CPI of 1 now, the ideal CPU is 4.44 times faster. So this was our CPI decrease, but the speed up of the ideal CPU increase. So it was A. And many of you did choose it. All right. So what if we double the clock rate without changing the memory system? So let's look at this. So with faster clock cycles, our miss penalty is now twice as long because it takes twice as many clock cycles now to fetch the data. So our new equation, we just need to replace the miss penalty of 100 with 200. So we have our total number of cycles stalling from memory is 6.88 times instruction count. So then with our new overall CPI of 2 plus 6.88, we have 8.88. Before it was 5.44. And now if we divide them, and this times 2 is because the clock cycle here is twice as much, right? We have 1.23. So we are a little bit faster. All right. So average memory access time. So a hit time is also important for our performance because with larger caches, we could affect our clock cycle time or require multiple cycles in order to even get a hit. Look at this on the homework. We will see that the cycle time is defined by hit time. So we also have this metric average memory access time. So this is the hit time plus the miss rate times the miss penalty. Here's an example. So if we have a CPU with a 1 nanosecond clock, we have a hit time of 1 cycle and a miss penalty of 20 cycles and a cache miss rate of 5%. Our average memory access time is 1 plus 5% times 20 gives you 2. So it's on average, every time you encounter a memory instruction, it will take you 2 cycles rather than 1. All right, so how can we improve cache performance? So this was our cache performance equation, right? So some ways that we can improve it is decrease our miss rate, right? Or we can try and decrease our miss penalty. Then here is, I'm just going to touch on this because I want you to be able to work on the homework. So we have covered a direct map cache. So every memory block goes to exactly one place. It's easy to find. You have your cache index is just going to be your block address, modulus, the number of cache blocks, and you use it as the index to the reference rule, right? But there are other caches. So you can have a fully associative cache. So a memory block can go into any cache entry in the vault, no index bits. So this is going to give you a lower miss rate because you have less conflicts. But now it's going to be more difficult to find because rather than knowing exactly what index location to check with the direct map, now I have to check every single location. Okay. So I have much larger tags because I don't have any index bits. So I need to compare with all of them. This might take some time to do my comparisons to find it. So my hit time might be low, but my miss rate should be low. And then there's also set associative caches. So this is rather than fully associative where any memory location can go to any index in the cache. This is any memory location can go to n different places. So this is going to be in your homework. So you just have to, if you have a two-way set associative cache, that means that for every index, now you have 2 different cache blocks to check. Okay, and this is also going to affect the size. So that is all for today. We will come back to set associative caches, but you should be able to do all of the homework. The homework is going to be due
May 1st.
Yeah, May 1st, the next Monday.
Just to make sure.
You'll never think. Okay.
Just to make sure. We end up with the same good. It's a game.
Yeah, I'm thinking. Yeah, we should take it later.
Okay,
Yeah. Hey.
and leave off here. I just wanted to review this real quick. Refresh your memory. So, what we had covered so far is a direct map cache. So every memory block goes to exactly one block index in the cache, so we know exactly where to look. So that makes it very easy to find. and it's very easy to calculate what is the index that the block should belong to. And we can just compare the tag and the valid bit, see if the valid bit is valid, and we'll know very quickly if our item is in the cache or not. But that's very restricting. So another type of cache is a fully associative cache. And in this case, a memory block can go to any of the cache entries available. So if the cache is not full, you will be able to put it into the cache. And this makes it more difficult to find, because now rather than just checking one place, or if we have a cache hit, we have to check every single location, as it can be in any location. So this could lead to longer hit times. And we need to do more comparisons. And another thing is that you might want to have a smaller number of like block locations, because we have to check all of them compared to the direct match cache. Right, so that's a fully associative cache, but we don't have to go all the way fully associative. We can do set associative. So set associative, rather than being able to go to any place in the cache, it would only be able to go into n different places in the cache. So if n is going to be the number of sets belonging to a single index entry. So we again will have the index, so we know exactly what row to look at. But now within that row, we need to know, is it in the first set, the second set, or so on, or none of the sets? So we have to check n different places with the tag, and if there's valid bits. And now we're going back to where we can only go to a unique set. But within that set, there could be n different blocks. So we have to check, is the block that we're looking for in one of the blocks of the set? Right? So this is going to be our address again. And we can search all of the entries in a given set all at once. Same with the fully associative though, but it does make our comparator larger because we have to compare with all of them. So here's a few examples of how we can have this associativity. So here's one way set associative. This is direct match, right? Every index, there can only be one block. And here we have two-way set associative. So for each index, now there's one block. So there are tag and the data, two blocks, tag and data. And then here's four-way. So 1, 2. This is tag data, tag data. So 1, 2, 3, 4. And there's two different sets. And then this is 8-way set associative. So there is no index anymore, right? And any data can go into any one of these locations. Right? So what is the cache index for address 12? Well, what would it be for here? How many locations are there? So what do you do with address 12? Block address?
Module.
So what's 12 modulus 8? 4. Okay. So same thing here. How many how many sets do we have?
4.
So what do we do with the 12?
1.
Okay, so what is that?
0.
So it goes to set 0. So it can go either here or here. And If this is empty, we'll just put it here. If this is full and this is empty, we can just put it here. If they're both full, then we have a choice. And we'll talk about that later. What about for this four-way?
The modulus 2, so it would go in 0.
Yeah, it would go into, and it can go here, 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 or here. Whatever is available, or if there's nothing available, we should evict. We should decide which one to evict. And then 8-way set associative, any of them. There is no index to calculate. So here's an example. So we have a cache size of 64 kilobytes. It's 2-way set associative, and we have one-word blocks. So which bits in a 32-bit byte address are used for our cache index? Which bits are the tag? Here we're going to go over this. So we have 64 kilobytes of total memory space, and we have 4 byte blocks. So we're going to have 16,000 blocks. But we are 2-way set associative, so we only have 8,000 sets. Because now for every index, we can store 2 different things. So in terms of how many locations we have, it's cut in half. So this is how we can calculate how many locations we have based on what is our total cache size, what is our block size, and what is our associative. And then because we have a 4-byte block size, we have 2 offset bits because it's byte addressable, right? Because we need 4 bytes to equal 1 block. And then with 8,000 sets, we just need to take log base 2 of the 8,000, and the ceiling of that is 13. So we need 13 index bits, 2 offset bits, and that leaves us with 17 tag bits. So this is all the same. The only thing that we now need to do is, once we have the blocks, the number of blocks, we need to divide it by the associativity to give us the number of sets. Everything else is the same. Right? Okay. So here is another example. So same overall size, 64 kilobytes. Again, 2-way set associative with a 32 bytes block. So which bits in a 32-bit byte address are used for our cache index, and which bits are the tag? So let's do this again. So we have 64 kilobits, and we 32 bytes, kilobytes, and then 32 byte blocks. So we have 2,000 blocks, right? And then 2,000 blocks, we divide it in 2 to get us the number of sets. So this is our number of locations that we need to be able to index with. So 2,000 divided by 2, 1,000 sets. And then since we have now 32 byte blocks, we need 5 offset bits because we're byte address. Our block size is much larger. And then how do we get our index bits? Just go on to the next slide. How many places do we need to be able to index into? Someone? 1,000, yes. Because we have 1,000 sets. So what do we do to figure out how many bits we need? If we need to be able to reference 1,000 places. Yes.
Log base 2.
Log base 2 of,
1000.
and that is
10.
8 is 256. Yeah, 10. 10 index bits. Make sense? Okay. And then the last thing is we have 32-bit address, minus 5 offset bits, minus 10 indexed bits, 17 packets. All right. So for set associated caches, we have n locations for a block. And our cache is a number of these sets. And each set contains n different entries for those blocks. And any memory block goes to a unique set. So we know which n entries to search through. And it can be placed in any entry of that set. Okay? So if I'm mapping to 0, I can go here or here. That's it. I only need to check this tag and the valid bit here, as well as this tag and the valid bit here. So how can we determine if the block is in the cache? Well, we get the address of the set that it belongs to. So we take the block address, modulus, instead of the number of locations in the cache, this is now the number of sets in the cache. Because although this is 8 data locations, there's only 4 sets, right? So that is what changed. And we just need to search all entries in a given set. And we can do this in parallel. Because we have access to the tag, we have access to this tag at the same time. We don't need to do one comparison, and then if that's wrong, then check the other. We can just check them both at the same time. Same thing with this. We have all of this data available to us, so let's just check them all at the same time. It'll be faster. All right, so that was this set. Now we can go on to the next set.